A Coast Guard ship receives a distress call. A sailboat is sinking, and the only information is 2 compass bearings from a checkpoint. Vector components turn that into an exact distance and heading. Today we solve 4 problems: magnitudes, navigation, a hidden quadratic, and points on a line, all with components. Every problem today uses the same toolkit. Write a vector by its components along I hat, j hat, and k hat. The magnitude is the square root of the sum of the squared components. Vectors add and subtract component by component. Never add magnitudes directly, unless the vectors are parallel. A unit vector is the vector divided by its own magnitude, and the position at distance r and angle theta from the positive x-axis has components r cosine theta and r sine theta. Master these 5 moves and every problem in this video reduces to arithmetic. We start with 2 3-dimensional vectors. Vector A is 2i hat minus 3j hat plus 7k hat. Vector B is 5i hat plus j hat plus 2k hat. We want 6 things, both magnitudes, the sum, the difference, and the unit vector along each direction. Pause here and try all 6. For the magnitude of A, square each component, add and take the square root. 2 squared is 4, negative 3 squared is 9, 7 squared is 49. The total is 62, so the magnitude of A is the square root of 62, about 7.87. Notice the negative component squares to a positive. Magnitudes are never negative. For B, 25 plus 1 plus 4 is 30. So the magnitude of B is the square root of 30, about 5.48. For the sum, add component by component. 2 plus 5 is 7. Negative 3 plus 1 is negative 2. 7 plus 2 is 9. So the sum is 7i hat minus 2j hat plus 9k hat. For the difference, subtract component by component. 2 minus 5 is negative 3. Negative 3 minus 1 is negative 4. 7 minus 2 is 5. So the difference is negative 3i hat minus 4j hat plus 5k hat. A common mistake is adding the magnitudes. 7.87 plus 5.48 does not give the magnitude of the sum, because the vectors point in different directions. Finally, the unit vectors. Divide each vector by its own magnitude. A hat equals 2i hat minus 3, j hat plus 7k hat, all divided by the square root of 62. B hat equals 5i hat plus j hat plus 2k hat, all divided by the square root of 30. Dividing by the magnitude scales the length down to exactly 1 while preserving the direction. These 6 results, 2 magnitudes, a sum, a difference, and 2 unit vectors, all came from the same component data with pure arithmetic. Example 2 is a rescue. A Coast Guard ship sits 35 kilometers from a checkpoint 52 degrees north of west. A sinking sailboat sits 24 kilometers from the same checkpoint 18 degrees south of east. How fast and in what direction must the Coast Guard travel? Pause and try it. The key move is converting compass bearings into standard angles. Put a checkpoint at the origin with positive x pointing east and the positive y pointing north. North of west means measure 52 degrees up from the west axis, so the standard angle is 180 minus 52, which is 128 degrees. South of east means 18 degrees below the positive x-axis, so the second angle is negative 18 degrees. A common mistake is plugging compass angles straight into cosine and the sine. Always convert to angles measured from the positive x-axis first. Now compute the components. R1 equals 35 times cosine of 128 degrees in x and 35 times sine of 128 degrees in y. That gives negative 21.5 kilometers times I hat plus 27.6 kilometers times j hat. R2 equals 24 times cosine of negative 18 degrees in x and 24 times sine of negative 18 degrees in y, which gives 22.8 kilometers times I hat minus 7.4 kilometers times j hat. The vector the Coast Guard must travel runs from its own position to the sailboat, that is R2 minus R1. Subtract the components. 22.8 minus negative 21.5 gives 44.4 kilometers in x. Keep in mind, we use the full precise values here, so the rounded display digits may look slightly off. Negative 7.4 minus 27.6 gives negative 35.0 kilometers in y. The distance is the magnitude. The square root of 44.4 squared plus 35 squared, which is 56.5 kilometers. The heading is the inverse tangent of the y component over the x component, inverse tangent of negative 35 over 44.4, which is negative 38.3 degrees. Negative means below east, so the Coast Guard heads 38.3 degrees south of east and travels 56.5 kilometers. Example 3 needs a bit of algebra. Two vectors add to a resultant C with magnitude 26.5. The magnitude of B is exactly twice the magnitude of A, and the C makes a 41-degree angle with vector A. Find each magnitude and the angle between the two vectors. Pause and try it. Now choose your coordinates wisely. Point vector A along the positive x-axis. Then A has no y component, and we know C's components immediately. Cx equals 26.5 times cosine of 41 degrees, which is 20. Cy equals 26.5 times sin of 41 degrees, which is 17.4. Since C equals A plus B, Cx equals Ax plus Bx. And because A has no y component, Cy equals By, so By is 17.4. Now use the magnitude condition. Bx squared plus By squared equals 4 times Ax squared. Substitute Bx equals Cx minus Ax. That gives the quantity Cx minus Ax squared plus Cy squared equals 4Ax squared. Expand it out, Cx squared minus 2, Cx Ax plus Ax squared plus Cy squared equals 4Ax squared. But Cx squared plus Cy squared is just C squared. Rearranging gives a quadratic 3Ax squared plus 2CxAx minus C squared equals 0. Apply the quadratic formula. Ax equals negative 2cx plus or minus the square root of 4cx squared plus 12c squared, all over 6. Plug in the numbers. Negative 40 plus or minus the square root of 1600 plus 12 times 26.5 squared, all over 6. We chose Ax positive, so take the positive root. Ax equals 10.0. Then Bx equals Cx minus Ax, 20 minus 10, which is 10. The magnitude of B is the square root of 10 squared plus 17.4 squared, which is 20.0. Exactly twice the magnitude of A, 10.0, just as required. That check confirms the solution. Finally, the angle. Vector B makes an angle with the x-axis whose sign is by over the magnitude of B, 17.4 over 20. The inverse sign gives 60 degrees. Since A lies along the x-axis, the angle between A and B is 60 degrees. The last example builds a general formula. 2 points P1 at coordinates x1, y1, and P2 at x2, y2 are joined by a line segment of length d. We want vector A running from the origin to the point on that segment sitting a distance little a from P1. Pause and set it up yourself. Let R1 and R2 be the position vectors of the 2 points. The difference R1 minus R2 runs from P2 to P1, divided by its length d to get the unit vector pointing from P2 toward P1. Here d is the square root of the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. Now define a connector vector S from the tip of vector A to P1. It points along that unit vector and has length little a, so S equals little a over d, times R1 minus R2. Going tip to tail from the origin, R1 equals vector A plus S. Solve for the unknown. vector A equals R1 minus S, which is R1 minus little a over d times R1 minus R2. Collect terms, vector A equals the quantity 1 minus little a over d times R1 plus little a over d times R2. This is a weighted average of the two position vectors. Check the extremes. When little a is 0, we get R1, so the point sits at P1. When little a equals d, we get R2, so the point sits at P2. In components, vector A equals x1 plus little a times x2 minus x1 over d. In the i-hat direction, plus y1 plus little a times y2 minus y1 over d in the j-hat direction. For problems, one method. Components turn vector geometry into arithmetic. Magnitudes come from squaring and adding. Sums and differences work component by component. Compass bearings become angles from the positive x-axis. Relative positions are differences of position vectors. Distance from the magnitude. Heading from the inverse tangent. Whatever the setup, 3 dimensions, rescue navigation, unknown magnitudes or points on a line, resolve into components first, and the rest is algebra. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.